I'm hearing you, Sam.
All right, cool. All right. Hi, everyone. This is Moses Sampal, part of Quantum Computing India. So today marks a very interesting day for us because we'll essentially be starting something called QCI Juniors. And as a prelude to that, we have Shakti Ganesh with us. He's a 16-year-old kid who has been interested in quantum computing, and we'll get to know his journey of like why he became interested in that. And today we'll essentially be talking about Untitled Cat, from there a little bit of quantum computing as well. So that's the 4 to 5 agenda, and 5 to 6 is implementing Shaw's algorithm and Quizkit by Shadab. It's a continuation of his last week's session. Um, so for people who are new to quantum computing India, I'm going to take like a couple of minutes to explain why we started and what we are trying to do. Now, Quantum Computing India is a community for all quantum enthusiasts in and around India, basically. So the way we wanted it to be different right from the beginning was not just to build a community around tech, but we wanted to look at the policy angle and the science behind it, right? At the end of the day, it really comes down to that. And storytelling. So the reason why we have art professionals is because storytelling is very important in any technology. We have lost, like, kind of left the bus in terms of previous cutting edge technologies, I would say, right? Like, be it your blockchain, be it cryptography, like, this was always at an arm's length for a common man to understand what these technologies really mean. If people don't understand what these technologies are, they cannot leverage these things, right? Art becomes very important as well. So with that, we started one. Now, over the period of last few months, we have structured ourselves across two different pillars of knowledge series and hack series. So knowledge series is what we have been doing on Saturday evenings, 4 to 6. We'll essentially get an academician or a practitioner, and they'll be imparting knowledge to us. And that's the whole point of knowledge series. Now, the hack series is where we are going to be using the learnings and creating something. Now, for example, the hack series 1 was around quantum finance. We started with volatility modeling, but then now we have structured ourselves into two different things over there. One is volatility modeling, and the other thing is options portfolio optimization. Now, both these things are very relevant, and this is one of the uh, fastest industries to adapt quantum, right? Because high frequency trading, those kind of things have always been there in finance. So it's easy for us to at least replicate what's happening at a classical level into the quantum part. And a bunch of our community members are working on that. So that's how the knowledge series and hack series come together, right? So you learn and practice. So that's how we learn anything. Now, the other thing is the community itself holds all of us together. So that's precisely how we have structured ourselves. So Saturdays 4 to 6, and the hack series kind of happens at on a monthly basis. So, for example, in August we have set aside the entire month for cryptography. So we are going to be starting with the basics of cryptography, and then some of the most renowned or known classical cryptographic algorithms, be it your not Shaw's algorithm, be it your hashing algorithms or AES encryption. Those kind of cryptography algorithms will be discussed. So that's in August 2nd week. And August 3rd week, we have Dr. Wood will be talking about quantum. Basically, now that we understand classical cryptography and how it's being implemented in classical computing, ideally by August 2nd week. So third week, we'll slowly dip our toes into quantum cryptography. And then fourth week is by QNU Labs co-founder. Now, she again comes with a lot of experience in information science, quantum information science, and quantum security. If you guys know QNU Labs is based out of Bangalore again. They are into quantum key distribution. So one of the ways or the early adaptations of quantum cryptography in the real world would be through quantum key distribution. Yes, please mute yourself when you join. So once these 4 sessions are done, then the 5th session is where we'll be trying to find out what's the use case that we can work on, right? So as you have seen, like first week, basics of cryptography. Second week is implementing cryptography in classical computing. Third week is intro to quantum cryptography. Fourth week is how the existing market is looking at quantum cryptography. And the 5th week is where we'll be discussing different use cases, and we'll pick 1 or 2, depending on the interest levels within the community. We'll take 1 use case or 2 use case. We'll structure ourselves into different teams and we'll start working on these. Okay. So that's how the whole knowledge series and hack series will come together. If you guys have any questions, I'll take it up, or we can directly jump into Shakti's question about Schrodinger's cat. All right, cool. Shakti, are you ready?
Yeah, I'm ready.
All right, perfect. Why don't you start sharing your screen?
Okay. Okay.
All right, perfect. All right, good luck, Shakti.
Okay. Thank you, Sam.
All right.
And thank you for that encouraging introduction. And I also want to thank the members of QCI who have given me this amazing opportunity to express my passion and my enthusiasm for quantum computing. Myself, Shakti Ganesh, I've just recently finished my SSLC examination and I'm waiting for the result. And today we're going to talk about Schrodinger Cat and also about quantum computers. Okay, so first let me talk about how I got introduced to the word quantum. Now, I first got introduced to the word quantum when I watched the movie Ant-Man, but I was just 11 years old at the time. So I didn't know much about the word quantum or any of those things. So I thought it was some mumbo jumbo which the movie directors made up for the sake of the story. But when I asked my father, who is also my mentor, about this, he told me that it actually exists. Not the quantum realm per se, but the term quantum and those things, they do exist. So I got interested. I wanted to know more about these things. And like most of you, I watch a lot of movies, and I got my enthusiasm mainly from the movies. They are the one which sparked that fire in my heart to learn more about quantum computing. And then fast forward 4 years, I went to the theater to watch Avengers Endgame, in which the main focus is the heroes enter the quantum realm to save the world. So quantum was the main focus of the movie. And then after watching this movie, I wanted to learn more about quantum computing. So I came across another movie called as Transcendence. And in this movie, the basic premise is that the main character who's after his death, they transmit his consciousness into quantum computers so that he can fulfill his dream even after he is physically dead. And they also talk about the power of quantum computing, saying that they are really astounding. And after watching this movie, I started to learn more. And when I was researching and exploring about quantum computing, I always came across this word called Schrodinger's cat. And excuse me, can you please mute? Hello?
Yeah, 1 second, Shakti. I'm going to mute.
Okay.
Okay. All right, go on.
Okay. after watching all these movies, I started exploring more about quantum computing, and I came across this word called Schrodinger's cat. Now, I am pretty young, so I don't know that much about quantum computing. So when I heard the word Schrodinger cat, I immediately related it to Tom and Jerry because I didn't know much about it. But when I explored it further, I realized that it was much, much more interesting than a cartoon. And I learned that it was a thought experiment which was related to quantum physics. And it was devised by an Austrian physicist named Erwin Schrödinger. When it happened during the discussions with Albert Einstein and other scientists. Now, let's talk about how we came to this stage. How and why did Schrödinger come up with this thought experiment? For that, we have to go back to, and before that, let me just talk about Schrödinger. He was, as mentioned earlier, he was an Austrian physicist who contributed to the wave theory of matter and to other fundamentals of quantum mechanics. And he also received a Nobel Prize in 1933, which he shared with a British physicist named P.A.M. Dirac. And he has worked on new quantum theory, creation of wave mechanics, unified field theory, and perception of color. Now, let's talk about how we came to this stage and how and why did Erwin Schrödinger come up with the thought experiment. For that, we have to go back to 1927 to the fifth Solvay conference. During this conference, there was a debate between Einstein and Niels Bohr on the behavior of light. Now, many scientists believe that light is behaving as a particle, while few scientists believe that light is behaving as a wave. Now, as an answer to this, Max Planck proposed that light is not. Before this, we used to think that light comes in a continuous stream, but Max Planck proposed that light comes in definite proportions, as you can see in this diagram. And he named these proportions as quanta. So this is one quanta of light, and this is Planck's formula for energy. Now, does this look familiar to everyone? Does this look a little familiar to anyone? Einstein's formula, that is E is equal to mc square, is based upon this.
Ganesh Payyan.
Hello? Yeah? Okay then. And Einstein and Bohr, they were rivals in a professional standard, but leaving the profession, they were pretty close. Now, the first serious attack by Einstein on the orthodox conception took place during the fifth Solvay International Conference on electrons and photons in 1927. And Bohr wrote an article titled Discussions with Einstein on Epistemological Problems in Atomic Physics. Now, here's an interesting incident which happened between Niels Bohr and Albert Einstein. Now, Bohr was facing away from the door and saying Einstein several times as if he was being summoned by a genie. While Einstein certainly came into the office, before Bohr could turn around, Einstein helped himself to some of Bohr's pipe tobacco. When Bohr did turn around, Einstein explained that his doctor had ordered him not to buy any more tobacco, but there was no injunction against his stealing some. So normally we would expect scientists to be stiff and humorless, but Einstein has a good sense of humor, and I really like that about him. Now, here's another important quote by Einstein. It says that quantum mechanics is very worthy of regard, but an inner voice tells me that this is not yet the right track. The theory yields much, but it hardly brings us closer to the world one's secret. I, in any case, am convinced that he does not play dice. This was a very famous quote by Albert Einstein. And now let's talk about the history of Schrodinger cat. Now, as mentioned earlier, it was devised by an Austrian physicist named Erwin Schrödinger. in the year 1935, Erwin Schrödinger published an essay titled "The Present Situation in Quantum Mechanics" as an answer to debate on wave-like behavior of particles. Now, according to the thought experiment, he told us to imagine that a cat is locked up in a steel chamber along with the following devices, that is, the cat and the Geiger counter, which will release acid when the counter ends, and a radioactive atom, which will decay and will activate the Geiger counter. And the acid is a deadly poisonous acid, so it will kill the cat when it's released. Now, until we open the chamber, we don't know whether the cat is alive or dead. So, what is happening inside the steel chamber? Now, as mentioned earlier, there was a radioactive atom which was holding the liver. That is, which if the liver is released due to the decay of radioactivity, the hammer would hit the glass bottle which contains that deadly acid, and it would dissipate poisonous gas when it's broken. Now, what was the probability of the cat to be alive? Now, we don't know when the decay will cause the liver to release the hammer and break the glass bottle. We don't know whether the cat himself would play around and break the glass bottle. Now, what can we say about the cat? Schrodinger told that the cat was both alive and dead. Now, I know this is confusing. How can a cat be both alive and dead at the same time? Now, I would like to do a small demonstration. So I'm going to switch on my camera. Okay, so I'm going to put up a poll. I'm going to toss a coin here. I want all of you to guess what would it be, heads or tails? Okay.
Shakti, can you stop sharing so that we can all see you in the main screen?
Okay. Yeah.
Yeah, better.
Okay. Now I'm going to toss the coin. I want you all to guess. Will it be heads or tails? Okay. 1. Now tell me, is it heads or tails? Can you guess?
It's
Well, when I'm holding it like this, how can it be sure that it's heads?
Both of it.
Yeah, this is what Schrodinger told, that the cat is both alive and dead. So this was just a small example, but there are 2 more examples to this. Let me show that too. That is, when a dice is rolling, and a Hindu god whose name is Ardhanarishwar. Hope you know. Okay. Now, how did the scientific world respond to this thought experiment? Now, they all realized that Schrodinger's cat was simply a teaching tool that Schrodinger used to illustrate how some people were misinterpreting quantum theory. And he also wanted to show that how some simple misinterpretations of quantum theory can lead to absurd results which do not match with the real world. They are that absurd. And Einstein also congratulated Schrodinger with his thought experiment. And he told that this interpretation is, however, refuted most elegantly by a system of radioactive atom, Geiger counter, amplifier, plus charge of gunpowder, plus cat in a box, in which the psi function of the system contains the cat both alive and blown to bits. Now, is the state of the cat to be created only when a physicist investigates the situation at some time? So what they're telling is, if we don't investigate the situation, the cat will be both alive and dead. It's only when we investigate the situation, we get a definite state. This is what Einstein told. And what does Schrodinger cat do? Now, as explained earlier, we keep a cat in a steel chamber with a device that had a 50% chance of killing it for an hour. Now, we would not know if the cat was dead or alive without opening the box first. So, in a sense, the instance before we open the box, the cat is equal parts alive and dead at the same time. This was his theory. Now we know. Now, what did I understand from Schrodinger's cat thought experiment? I took it like this. I I I took it like they are using this thought experiment to explain something happening inside an atom or an electron. Now, let us compare the component individually with both an electron and the Schrodinger cat experiment. Now, we can take the cat as the spin energy of an electron, while we can take the rest, that is the gunpowder, Geiger counter, radioactive atom, as the uncertain part of the whole system which can affect the spin energy of the electron. Now, as the Schrodinger cat had equal probability of being dead and alive, the spin energy of an electron can have equal probability of having a specific position out of infinite position. Now, since the spin energy of an electron can also behave like a Schrodinger cat, it may stop us from measuring the definite position of the electron. Now, and I also learned that we can use linear algebra to find the position of the electron. Now, let's take it like this. Linear algebra can help us to add vectors and find the result of the addition. Now, consider that the spin energy of an electron is a vector, and each transition of spin energy can be considered to be a vector of complex number as represented in the Bloch sphere. You can see here. And at any point of time, you can measure the spin energy using the formula given. You can see it here. And the only challenge, as mentioned earlier, is that the spin energy of the electron behaves like a Schrodinger cat, which has equal probability of stopping us from measuring it. And I am not completely sure, but I read that we can use an entangled qubit as an ancilla for measuring the spin energy of an electron without affecting the processing qubit. But I still don't understand what it means entirely. So I have to learn this part later. So forgive me, I can't explain it entirely. Now, Schrodinger understanding. This was something which happened while my mentor was explaining these concepts to me. He was explaining it with a great deal of enthusiasm and he was very energetic. It was obvious that he loved the subject. And after explaining all these things, he asked me, Shakti, did you understand? And I didn't want to disappoint him. So I told him I understood it the Schrodinger way. That is yes and no. I expected a frown or scolding, but he laughed it off and he showed me this. This is a quote by Richard Feynman, who's a Nobel laureate. He says that if you think you understand quantum mechanics, you don't understand quantum mechanics. And I remember Professor Kunal talking about this quote in one of his sessions of QCI. So that's why I thought of this. Thank you for that. And now let's talk about what is quantum physics. And now, quantum physics is a part of quantum field theory, and it's a fundamental theory in physics. It describes physical properties of nature on an atomic scale that is very small. And this is different from the classical physics which we used to study in high school, because the classical physics describes many aspects of nature at a macroscopic scale, that is the ordinary scale which is visible to a naked eye. While quantum physics explains the aspect of nature at an atomic and subatomic scale, for example, like electron, neutron, proton, and quarks. Now, how can we apply quantum mechanics in our real life? You see, there are many examples of technology that apply quantum mechanics, and there are much exciting research currently happening to develop further application of quantum mechanics. And these are some of the examples of application of quantum mechanics. We can use those in atoms and molecules, nuclear physics, subatomic particles, and quantum optics. And in quantum optics, we can use it in quantum computing, which is the main focus of the day, quantum computing. Now, what is a quantum computer? Let's talk about that now. Quantum computers are using quantum mechanical phenomena such as superposition and entanglement. Superposition, it was explained using Schrodinger Cat experiment, that is, an object can exist in two states at the same time. And quantum computers are using qubits for computation. Normally, we use bits in the classical computers, but we use qubit for quantum computers. And a qubit can be either 0 or 1, and 0 and 1, both at the same time, just like Schrodinger cat. After this, I was finally able to connect Schrodinger cats to quantum computers. And it took me a great deal of time and confusion to get to this point. Now, you can see the diagram of a quantum computer and the components. The components are analog electric converters, electric signals, a coolant because quantum computers require very low temperature to operate, and a fridge, and qubit signal amplifier, superconducting lines, vacuum, electromagnetic shielding, qubit amplifier, and radiation shielding. And here we have the quantum processor. Okay, so how can a qubit be used? Now, I'm still trying to understand this more clearly, but in simpler terms, if we measure the position of spin inside an electron, we can arrive the result of a computation. As we know already, measuring a qubit, which is in coherent superposition, is not possible. Now, imagine that we added a trigger in the door of the steel chamber where we kept our famous Schrodinger cat. Now, the real challenge to be engineered, but it's not too difficult to achieve. In one of the experiments, scientists were able to measure the coherent superposition by adding an entangled qubit. Now, all the measurements was done in this extra qubit. So, actual computation will be done to another qubit inside the system. Since they are both entangled, we would get the result of the qubit inside the system when we measure the extra qubit. Now, my analogy to understand this, because I mostly understand things using pop culture reference. So now for this analogy, I'm using Tom and Jerry. Now let's think that Tom is in coherent superposition and Jerry is entangled with Tom. Now we cannot directly see Tom as he's blocked here, but we can observe Jerry and predict where is Tom inside the steel chamber or what is he doing. So if you go to the next slide, we can see that Tom is identical to Jerry. Now we have a question. What physical system are available to build such a qubit? There are many platforms for building qubits, and one of the popular system is diamond. You see, a vacancy in the atomic structure of a diamond will behave like a Schrodinger cat, and it is being used as one of the qubit in the qubit building approach. And this is not the only system, because there are few others like this. I have given 3 examples here, that is neutral atoms in optical lattices, nuclear magnetic resonance based quantum computers, and electrons on helium. Now, let's ask this. Are there quantum computers? Yes, there are very few working quantum computers in the world right now. And I would like to share the image of the most popular 4 quantum computers. And they are all owned by this respective company, that is IBM, Google, D-Wave, and Rigetti. Now, the quantum computer owned by IBM is called as Q System 1. And this quantum computer, it is available for the general public through a cloud platform. And it is one of the most widely accessed quantum computing platforms. The next one is owned by Google, and the system is called as Sycamore. Now, Google announced quantum supremacy in September 2019. And I think this announcement is an important catalyst for the hype on quantum computer. And Google says that its 54 qubit Sycamore processor was able to perform a calculation in 200 seconds. That would have taken the world's most powerful supercomputer 10,000 years. That would mean the calculation which involved generated random numbers, is essentially impossible on a traditional non-quantum computer. This shows us the power of quantum computers when compared with classical computers which we have in our home. Now, okay, and the quantum computer owned by D-Wave is called as 2000Q, and D-Wave was the world's first company to sell computers. However, they are called quantum annealers instead of quantum computers. In 2015, D-Wave's 2x quantum computer with more than 1000 qubits was installed at the Quantum Artificial Intelligence Lab at NASA Ames Research Center. And they have subsequently shipped systems with 2048 qubits. And in 2019, D-Wave announced a 5000 qubit system, which will be available mid-2020, using their new Pegasus chip with 15 connections per qubit. And then finally, a quantum computer owned by Rigetti, which is called as Aspen 8. By February 2016, the company had already begun testing a 3 qubit, that is quantum bit, chip made using aluminum circuits on a silicon wafer. And by spring of 2017, the company was testing 8 qubit computers. And in June, the company announced the public beta availability of a quantum cloud computing platform called Forest 1.0, which allows developer to write quantum algorithms. Now, in a quantum computer, where is the quantum processor located? You can see here it's located at the bottom. And as mentioned earlier, the quantum processing elements are operating at subatomic level in a nanometer scale. And they need to be kept under minus 273 degrees Celsius to operate properly. So they need a gigantic infrastructure for cooling purposes only. Hence, that's why the quantum computers are very large, as we've seen in the images before. Now, what is my passion? Now, talking about all this, it's very exciting for me because it all started with watching one movie, and it has come to this. And even before watching the movie, I was really passionate about science and mathematics. They were my favorite subjects when I was studying in school. So, to come into the quantum computing career, I will pursue engineering from IIT or IISc, and I will start studying these topics, that is Python programming, Qiskit, linear algebra, complex number, and Hilbert space. And QCI is already taking courses related to Qiskit, which I've been attending for a few weeks, but I didn't understand it completely. And now, why do I have to learn Hilbert space? Now, I still don't understand exactly why, but Hilbert space helps us to calculate in n dimensions, and Euclidean spaces are typically 2 dimensions or 3 dimension, and a Cartesian coordinate based graph is an example of Euclidean space. So I'll learn about Hilbert space in the future. Then, and complex number. And again, I'm having confusion with complex numbers, but the spin of the electron and the behavior of an electron cannot be easily represented and processed using real numbers. You have to use complex numbers for that. And then linear algebra. You see, the spin energy of an electron can be mathematically represented as vectors. We've previously talked about this, and the physical operations can be simulated using vector and matrix operation. And linear algebra is a starting point for all advanced mathematical concepts, which I need to learn to pursue quantum computing career. And the concepts linear algebra includes scalar, conjugate, vector, adjoint, matrix, and transpose. And why Qiskit? And I will start with Qiskit. Now, as as you all know, QCI team is conducting Qiskit training. It is from IBM, which is a pioneer in quantum computing. But this does not mean I will not learn other frameworks. I'll continue learning all major frameworks for quantum computing like CIRQ, Ocean, QCL, QHash, Forest, QGL, which is Julia language, Penny Henadu Strawberry, and OpenQASM. Now Python. Now we talked about Qiskit, and the IBM Qiskit is a Python framework, and Google CIRQ is also a Python framework, and Rigetti Forest is a Python framework. D-Wave Ocean and Microsoft, no, sorry, D-Wave Ocean is Python framework, but Microsoft QHash is not a Python framework. So it's obvious why I choose Python as one of the topics which I will learn in the future. But in addition to this, my father, he is using Python for data science. My mother is using Python for machine learning. And my brother is using Python for game development. And now I'm going to use Python for quantum computing. So basically we are a Python family. Everyone is learning Python. And with that, I would like to conclude my presentation, and I'm ready for Q&A. So you can ask any question you like.
All right. Thank you, Shakti. That was really interesting and well put together. I just have one question because you kind of went really fast in that slide. You can go back to the slide where we had that the Hindu god,
Oh yeah.
Arthanateshwar, right? Can you explain that, like the context behind that?
Yeah, the context. Yeah, I was thinking of examples of Schrodinger cat being both alive and dead, that is superposition, and I remember my mother talking about this god in some stories, but I don't remember exactly. So I just randomly remembered about that. So I thought maybe you could use this as an example.
Oh, so this god is a male and female at the same time, right?
Yeah, yeah.
Okay. All right. So that's the context. Huh. Cool.
Yeah, correct. Just a random thought I got while I was
very nice.
researching.
Very nice. All right. So there's a question in the chat as well. What's the field of use of this QC?
QC.
As in, are you talking about use cases of quantum computing, Jay Krishnan?
I'm sorry, but I didn't understand the question properly.
Yeah. Applications.
Applications, yeah. I know that we can use quantum computers for very complex calculations and all that, which cannot be performed by classical computers, but I don't know anything more than that.
Okay, great. One good thing about this whole presentation is that when you don't know something, yes, who's that?
So this is Vijay.
Yeah.
So I just want to talk a few minutes.
Sure.
So Shakti, first of all, congrats. So even I can say in the school level, what you have able to talk is really awesome, and it is a good foundation. I hope you will go a long way.
Thank you, sir.
So there are a kind of whatever you have put your learnings, just try to order that.
Okay.
So first, what linear algebra, Python, Qiskit, and if you go with that, I think now you have a good chance. Because of pandemic, everything is shut down and closed.
Yeah.
And IBM is, I don't know, you might have missed it. IBM has given an opportunity for 2 weeks of quantum fundamental Qiskit summer school.
Yeah,
it's
I remember
happening.
Yeah, I remember reading an article related to that, but
yeah, some limited people, but for a lecture, there is no limitation. Whoever registered, they can go with that. For lab exercise, first 2,000 entries only they are giving, but irrespective, anyhow, it is over. They are continuously giving those lecture notes or videos. So it is once you are comfort with that Python, you will be able to go with that. So you can play around Qiskit. It is not a much challenging one.
Okay.
So make your, because you said your family is a Python family. So I don't think any challenge in Python getting into this thing.
Yeah.
Okay. And all the best. I guess it's a quantum is the future. Before the quantum computing realized it will take a long. 3 to 5 years. I hope you within that time you will be the master in this quantum. Even
Yeah,
honestly,
I hope to be.
older than me, you know, and explain in a very layman's view. Okay. And
Okay.
come to that, Sham. So quantum applications, I can say, I am also kind of a bit of what to say, part-time learning in quantum, not full-time.
Okay.
So quantum, we can there are different categories, or quantum use cases can be applied in all the domain. But broadly, I will say optimization and machine learning and
Okay.
sampling. So these are
Okay.
the three ways IBM at least split into those quantum thing. So optimization, whatever kind of simple, the traveling salesman problem, or with a complex constraint, you want an optimal route. So for example, you can say, what is a Bangalore traffic with too many constraints.
Yeah.
So you want to be at one place with the traffic condition, fuel in this thing, and lot of constraints, and which is the best place for a delivery person to deliver pizza in a particular time interval. So you can apply quantum. This is a very simple example I am giving. So kind of, if you see this DSP, you can apply across many areas. It is what to say, from postal delivery to you are delivering pizza, kind of this delivery. These are all very simple example. Doesn't require quantum really, but for understanding,
we can use it.
Aircraft route itself, you can go with that. So kind of all complex application can be first converted into a quantum problem. The first step, I will say, you have to define that optimization problem, that classical problem, to be converted into a quantum optimal problem. So you have to choose which problem worthwhile to take it to quantum.
Okay.
Then you have to come, what are the constraints for those quantum? How to mathematically make that problem into a QBO problem. Unconstrained binary optimization, quantum unconstrained binary optimization problem. Then you will convert that into this is a kind of a multiple algorithm is there. I'm just giving one problem. So that you will convert into a Lysing-Hamilton. That is a mathematical equation. From that, it is a direct, Qiskit has a documentation available how to convert those equations into a programming. But unfortunately, we are lagging with the real quantum computer to run those things. Theoretically, we can go with, and even I have seen few weeks back from IAC, Bala is talking about what is it, Grover's algorithm. So all that, how we can break RSA. So all this thing has been that is a source algorithm. Source algorithm, though it is not theoretically practically implemented, but theoretically it is proven huge digits of number can be less than a few seconds can be factorized. So that is a threat to RSA. Something similar, every problem theoretically we can realize, but in a matter of time it will come to practical. So other thing I can say, quantum machine learning. So again, with the constraint of a currently available infrastructure, you may not be able to appreciate the quantum machine learning, but still there are kind of what is a part of quantum, you can say transfer learning or hybrid model. So pre-processing, you can be quantum, and then you will use a training model, traditional model, or you can pre-process using a traditional model. The output layer alone, you will introduce the quantum. So kind of
Mr. Vijay, sorry to cut you off.
Yeah, Shyam, please. I'm sorry I have taken much time.
No, it's okay. It happens usually. All right. So few other questions were there. Any real-time use cases? Yes, cryptography, QKD, which is quantum key distribution. So August 4th week, which is the 22nd of August, we'll have Dr. Anandita from QNU Labs, and QNU Labs has been working with quantum key distribution for the last 3-4 years at least, right? And if you guys can watch TechCrunch 2020, it was all about quantum, okay? So it has already started, at least in cryptography and finance. So if you look at like the industry research reports, it's quantum finance and quantum cryptography. These are the current areas where these are being used. Yeah, okay, cool. Any other questions? Right. Okay. QNO Labs. Thanks, Shadab, for answering these. And Shakti, this was lovely. Hope that we continue this, like Mr. Vijay was also saying, you know, and I'm sure, like, being part of KG's family, I'm sure, like, you're going to continue.
Oh, yeah.
Guys, any other questions? If not, we'll take a quick 5-minute break and come back with the Shor's algorithm implementation and Qiskit by Shadab. All right, so no questions. Thanks, guys, for joining. This is really encouraging for you know, people like Shakti, who's going to come and talk to us, right, in the future as well. So one thing that we are again planning is to have parallel sessions for juniors, and I would probably be learning from there because it's fun, and the way that Shakti had structured this based on pop culture references, that makes it really easy to understand. And I haven't seen an analogy of Tom and Jerry used in quantum. That was brilliant, Shakti. Good job.
Thank you, sir.
All right, cool. Guys, so it's 4:47 now. We'll come back by 4. Right. We'll come back by 4:55, and we'll start with Shor's implementation and Qiskit. All right.